Unit 7, which is a significant shift in thinking about these systems. So the shift from Unit 5 to Unit 6 was very subtle. It was how do you draw a root locus diagram versus how do you use a root locus diagram to design a system. The shift from 6 to 7 is anything but subtle. This is we're throwing Laplace away and we're just going into Fourier land. Okay, so Unit 7 will be a review of sketching frequency responses, and Unit 8 will be how do we use frequency responses to design systems. Okay, so it's kind of analogous. Unit 5 was how do you sketch something in the S-plane versus how do you use it in Unit 6. This is how do you sketch something in the frequency domain versus how do you use it in Unit 8. Okay, so the bridge from Laplace to Fourier, if you haven't seen this before, if you go back to your 228 notes, these are how we defined the Laplace transform, the unilateral Laplace transform, sorry. So this is the unilateral Laplace transform. And again, that's the Laplace transform that gives us all the nice things that we use Laplace for. That is initial conditions, ZIR and ZSR in one go. So the unilateral Laplace transform is the one we learn because it helps us solve initial condition problems. The Fourier transform, and then inconveniently, we use the same symbol here, even though these are two different functions. Okay, so I'm sorry, but I didn't make the rules. We call both of these capital H, whereas the Laplace is capital H of S, S being a complex number, versus capital H of omega, omega being a real number. Okay, so fundamentally these are two different functions, even though they get the same name, capital H. They're defined differently, right? Clearly the differences are in the lower limit integration and in the exponent up here. But my goal is not so much to highlight how they're different, but to highlight how they're the same. In particular, if little h of t is causal, all right, so go ahead and search, knock the cobwebs off the signal classifications that you learned in the first week of 228. If h of t is causal, and remember all that means is it starts to the right of the origin, then this lower limit doesn't actually matter. If h of t is causal, then I lose nothing by setting that to 0. Right, because I'm just chopping off a bunch of 0 stuff. Furthermore, if j omega is in the region of convergence of the Laplace transformation, then all I'm doing to get this is evaluating the Laplace transform within a point of its region of convergence, which is completely legit. Right? The region of convergence is literally the region of the S-plane that allows this integral to converge. So that means it's the good space. So what I'm doing is I'm taking a Laplace transform. This is, if you like, the Laplace transform, and I'm just evaluating it at a point in its domain. I mean a variable point, if you like, because omega is itself a variable, but I'm evaluating it along the imaginary axis. And because I'm evaluating it along the imaginary axis, then that is tantamount to evaluating it along a real variable, because the imaginary axis is j times a real thing. Okay, so this is the bridge, is that if all you're doing is considering causal systems, then if the system is stable, that's the other kicker, because that's how we get this usually. This means your left half plane poles. Then we can go from Laplace to Fourier lickety-split by taking the Laplace transform and evaluating it along the j omega axis. So this is, I mean, they're both also called transfer functions. That's the other kind of inconvenient thing here. This would be the Laplace transfer function. Wow, that's unacceptable even for me. This is the Laplace transfer function. And I think that you would be fine to call this the Fourier transfer function. But in order to keep things straight and to keep our transfer functions in Laplace land, I am going to refer to this as the system's frequency response. Mostly because it is what the system does to different frequencies. Okay, so that's my justification to try and clear up what's a transfer function. When I talk about transfer functions, I'm going to talk about Laplace things. When I talk about frequency response, I'm going to talk about Fourier things. And if the system is causal and stable, they're the same thing. Okay. So this function, this frequency response, this is again review. It tells us what does the system do to sinusoids when input. Fourier transform, Fourier series, they tell us that many of the signals that we like to analyze systems for are composed of sinusoids. So that's why everything comes back to sinusoids. You can talk about the amplification and the phase shift as what's called the magnitude of the frequency response and the phase of the frequency response, also sometimes called the argument, which is, I think, super confusing. This is sometimes called the phase, sometimes called the angle, and sometimes called the argument, even though I am going to refer to the argument of this function as literally the thing that goes in the parentheses. You will see in some math textbooks this operation called the arg of h. I don't know where that comes from, actually. That'd be an interesting history project. So that means that this function h is a complex number, which means you can also think of it as having a real part and an imaginary part. So these are the common decompositions, the polar form, if you like, and the Cartesian form. All this is to say is there's a lot going on, right? These are functions of a real variable. Get mapped to a complex thing. And so if you were to try and plot these, there are three real dimensions to think about. There is the domain, which is a real number line. And then there is the range, which is has a real dimension 2, because it has complex dimension 1. So I think that's why there are so many competing methods to represent frequency responses. The one that you're probably most familiar with is the so-called Bode plot, which takes technically not the frequency, but the log of the frequency, and generates two plots. And on the top, we usually see the magnitude of h in decibels and the phase of h. Okay, so this is the common, I think that's what you teach you in 212 and 228. But there's nothing magic about the Bode plot. It's just a way to visualize what the frequency response does over different frequencies. And that's actually what all three of these do. The Nichols plot takes a different approach. The Nichols plot actually plots the phase of h on the horizontal and the decibel version of the magnitude on the vertical. Okay. This means that omega is no longer explicit. This is now a parametric plot, but you're used to parametric plots by now. That was all of our root locus plots. And then Nyquist is kind of similar in that it's parametric, but Nyquist plots take the real part of h and put it down here, and the imaginary part of h and put it up here. Okay, so all three of these are trying to communicate the same thing. What does this function do at different frequencies? And do has multiple meanings. Do can mean, does it amplify or attenuate? And do can also mean, does it phase advance or phase delay? All of these three plots are the three leaders, I would say, in terms of visualizing the frequency response of a system. We are going to focus here. The textbook also contains a significant section on Nyquist plots, and that's because there are nice ways to interpret stability from Nyquist plots, but I don't think we're going to have time for that. So we're going to focus on the thing that you have seen before and give you a little bit more detail on it. But questions so far? Okay. So all of our transfer functions, all of our systems, provided their LTI, they can all really be described in terms of 8 what I call ingredients. So what do I mean by an ingredient? I mean a thing inside the transfer function. They can have constants. They can have zeros located at the origin. They can have real zeros, and they can have complex conjugate pairs of zeros. They can also have poles at the origin, or real poles, or complex conjugate poles. And that's the 7 kind of more common ingredients that you'll find. The 8th, and the one that doesn't get a whole lot of attention, is this kind of ingredient. So tell me, how would you describe this ingredient? E to the minus s times a capital T. What does it do? Or what thing in the time domain gives rise to this in the s domain?
Isn't that like a shift on the plot? The period, well, like in a unit step function, if it's like shifted over by
a delay.
one. Yeah, a delay or an advance.
Yeah, good.
Yeah.
So delays only, right? Because Laplace is unilateral, and Laplace can only handle time delays, not time advances. But yeah, so these are the 8 fundamental things, and any LTI system, you're only going to find these kinds of things. You can have multiples of them, right? That's why I've allowed for an arbitrary number of each of them. Or you can have none of them, right? So it's possible that the m's could all be 0, and we just get a 1 on top. And the t can be 0, so we just get a 1 out here. Okay, but in general, you can have any number of these 8 things. And importantly, you can't have anything that's not here. Okay, and that's an interesting way to look at it. Oh, my time's already up. Sorry, people. Ran over just getting into Bodhi plots here. We will pick this up on Wednesday. Thank you so much.